So again, I want to thank everybody for joining us here today on this 3D Systems webinar with our customer, Force India. Force India is a Formula One team based in the UK, and we're going to be sharing with you today how this team gains points with SLA 3D printing. Our speakers today will be Tom Sharon, that's me. I am the VP of Product Marketing for Professional and Production Printers at 3D Systems. And I'm very happy to have our guest, Paddy Houghton, with us today. He's the Rapid Manufacturing Leader at Force India. And I want to let you know that there will be a live Q&A session at the end of the presentation. And you can type your questions into the questions box in the GoToWebinar window. If you look in your GoToWebinar window, you'll see towards the bottom there's an area where you can type in questions. And you can type those at any time during the presentation or during the Q&A session at the end. And because of the number of people on the webinar, we don't open up the phone lines to everybody. So you type your questions in and we'll answer those verbally. I also want to mention that a recording of this webinar will be emailed to you sometime later today or tomorrow after we've been able to record the session and upload it for further watching later on. And so if you want to share this with your colleagues or anyone else after watching this today, you'll be able to do that by sending the link that we provide via email to anyone you'd like. So let me start with a quick introduction to who 3D Systems is. We make the ideal real, and we're both the originator of 3D printing and the shaper of the future of 3D solutions. And we're really proud to make these 3D solutions accessible, simple, productive, and gratifying so that you can transform your ideas into tangible outcomes. From engine prototypes to flight-ready aerospace parts, from a surgical trial run to medical implants, and from a designer dress to intricate confections, 3D Systems lets you make great things happen. We offer the broadest choice of 3D printers in the market. So we've got systems that are designed to fit your specific application and to fit your budget, all the way from sub $1,000 printers for the home up to $1 million plus machines that are high-capacity production systems. And we can print parts in a variety of different materials, including dozens and dozens of different kinds of plastics, a variety of metal alloys, including aluminum, titanium, stainless steel, so on and so forth, strong nylon parts. We can print in wax for casting patterns so that you can make metal parts indirectly from a 3D print. And again, systems run the gamut all the way from sub $1,000 up to more than $1 million. Now, as we talk about the different opportunities in 3D printing, we can really break things into 5 different broad application categories. And it's really important to think, as you look at additive manufacturing or 3D printing, what exactly do you want to get out of the technology? There's concept models, which are great for communication. There are functional prototypes, which are great for engineering validation and testing your ideas. You can create rapid tooling on 3D printers, which is great for pre-production. You can make production parts, of course, and we see that not only with metal 3D prints and SLS printing for tough plastic parts, but also SLA for precision plastic parts. And then the last category here is mass customized parts. And usually we see that in healthcare with dentistry, hearing aids, and a lot of other areas of healthcare that are really being revolutionized by 3D printing today. Now, today's webinar and what Force India is doing with SLA 3D printers really focuses around the functional prototyping side of things, where they're validating engineering and design changes. And Patty's going to talk about that in a lot more detail. So with that, let me hand it over to Patty. And I'm going to give you screen control at this point, Patty, so you should be able to advance the slides now. And feel free to go ahead and introduce Force India.
Okay, thanks, Tom. Hello, yeah, as Tom introduced me, my name's Paddy Horton. I'm the rapid manufacturing leader for Sahara Force India Formula One team. So yeah, I'll introduce Force India. So Sahara Force India is one of the fastest growing teams in the highly competitive world of Formula One. After entering the sport in 2008, the team has established itself as a strong competitor, producing inspiring, giant-killing performances and creating a loyal following of fans. 2014 was the best season in the team's history, and we're out to make 2015 even better. So to give you an idea of the progress we've been making, in 2008 we finished 10th in the Constructors' Championship. 2008 was our first year of competing. In 2009 we finished 9th, and in 2010 we finished 7th. 2011 we finished 6th. 2012 we finished 7th again. 2013 we finished 6th. 2014 we finished 6th. And in 2015 we've got our eyes on 4th, so we're hoping to continue the general upward trajectory since our inception. So for us, the challenge, Formula One cars are the fastest road course racing cars in the world, owing to very high cornering speeds achieved through the generation of large amounts of aerodynamic downforce. So our challenge here is to continue finding and adding downforce to the car to increase our lap speed. Maintaining an aerodynamic edge requires constant engineering and wind tunnel testing. So not only do we have to keep finding downforce, but we have to find it faster than our competitors do. So an example of a section of that challenge that we have, we'll use the front wing as an example. So on the slide here you can see a fairly basic image of a front wing, but I think it is very representative of what's going on. It's got all the key parts on there, such as the cascade, the main flap, the main plane, the turning vanes, and the end plates, and a little sort of indication of where the air is going when it hits the side of the front wing. So approximately 33% of the total downforce is provided by the front wing on a Formula One car. So we're constantly refining the design of the front wing of our race car. So both the front and the rear wings of an F1 car behave like an upside down aircraft wing. While an aircraft's wing is used to produce lift, the wings on these race cars are used to force the tyres down. This downforce allows the tyres to generate high levels of lateral force that then allow the car to stay on the track when taking a corner at high speed. The front wing, unlike the rear, does not just provide downforce. As it is the aerodynamic device that precedes the entire car, it is also responsible for manipulating the airflow behind it that reaches the rest of the race car. This airflow manipulation is of critical importance to the overall downforce levels produced by the entire car. Force India Formula One have a requirement to create thousands of prototype parts to test new aerodynamic ideas in their wind tunnel program. These parts must be produced quickly, sometimes just from hours from the idea to the part being tested. Now when we talk about being produced quickly, SLA technology allows us to build hundreds of parts on each build platform. A typical build time for a full platform would be something in the region of 48 hours. We can build individual parts though in just a few hours when it's necessary. The next requirement would be that they are stiff, so very little deformation at 112 miles an hour under an aerodynamic load can be tolerated. So when we're talking about the stiffness, we use 3D Systems filled materials, and these resins in the SLA machines, they have a dense ceramic filler that stops the plastic parts from shrinking, distorting or deforming when under wind tunnel conditions. the next consideration would be smoothness. So we want excellent surface quality with minimal finishing time required. So this is a layered technology, and it has a layer thickness of 0.1 of a millimeter. This means that our organic shapes appear smooth and need very little manual finishing. So I just have to move this down a tad. The next consideration would be accuracy. So we must be able to achieve better than plus or minus 0.2 of a millimeter on every component compared to intent. So the resolution of this technology is very, very high, and it has a laser spot size of 6/1000ths of an inch in diameter. That's 0.12 millimeters. So we can achieve just over plus or minus 0.1 of a millimeter in the XY plane, and with the layer thickness of 0.1 millimeters, we can achieve 0.1 millimeters in the Z direction too. So if you consider both of these parameters, we can comfortably achieve an overall tolerance accuracy of better than plus or minus 0.2 compared to the intended CAD data that we are given. And then another requirement is that they are strong. So we need our parts to be able to hold pressure within internal bores that are used for static pressure testing. So when we're talking about this in our world, the integrity of the parts that are being built using this technology is such that they can hold pressure. So the way the layers are bonded together, the 0.1 layers, they're bonded together, and it is such that the integrity is near perfect and no air leaks out at all. So we can design pressure tapped channels integrally into the parts and then carry out static pressure testing. On our front wing, this would be up to 5,000 pascals with no leakage. And then we need the parts to be tough. This material can be considered an engineering plastic, and we are able to do normal engineering fastening practices on these parts, such as threads and dowel joints. So when we're talking about the toughness, we're able to carry out lots of post-build engineering practices such as threading, doweling, drilling, machining and trimming. Due to the toughness and durability of the materials, we are able to plan to build one component and use it for multiple revisions. To meet all of our challenges, the solution is printing components with 3D Systems SLA machines. So we have 3 of the largest SLA systems. We bought them when they first come to market. They had a different name back then. They were called Viper Pros. And 3D Systems carried out a raft of improvements on that machine and then changed the name to the iPros, which is what you can see in the slide. The name and the appearance has now changed again to the ProX 950, which is what you would see on 3D Systems website today. We also have 2 mid-size SLA systems, the SLA 5000 system. We have had these 2 machines since 1998, and they have been building parts 24/7 since then, so you can see these machines are built to last. And we are using 2 3D Systems resins. We are using Acura Bluestone and Acura 60. So, a front wing end plate. This is an example of a part that we've printed using SLA, and we've used it in wind tunnel testing. It's made from bluestone resin. It has been finished in our model shop, primed and sprayed. So shown above is a picture of a front wing end plate, which we abbreviate to a FWEP. FWEPs are used on the tip of the front wing to manipulate and create pressure differentials. We use these pressure differentials to produce vortices, manipulate flow direction, and create forces and moments to try and deliver maximum pressure energy to the rest of the race car. Delivering more energy downstream allows us to use that energy to work the air to produce more front and rear downforce. An F1 race car can generate 3 times its own weight at 200 miles per hour, primarily due to the shape of the car that rapid prototyping has allowed us to develop. FIA rules allow us to test our wind tunnel at a scale of 60% with a speed of 50 meters per second, which is 112 miles per hour. The clearest illustration of the benefits of this technology to Force India F1 is that it allows us to repeatedly and robustly test endless iterations of ever more complicated shapes week after week in a wind tunnel operating at 112 miles an hour with minimal breakages. So to give you an idea of the tunnel testing process, aerodynamic ideas are initially simulated using computational fluid dynamics, which again is abbreviated to CFD, and that's a software package. CFD allows shapes to be numerically evaluated by a computer. If an idea still shows promise after CFD, the aerodynamic department will produce a survey of components based around this idea. The parts for this survey are designed using CAD and released for manufacture to our 3D printing department. We build these parts on our 3D printers. They are then finished in our model shop and subsequently tested in the wind tunnel. The different iterations in the component survey are not always visible by eye, such as the level of detail that we achieve. We would not be able to evaluate components of such detail if we didn't have our 3D printers. So beyond prototyping, we do not just use 3D printers for wind tunnel applications, we also use them for tooling. As Tom mentioned earlier, we can use them for tooling, in our case for carbon fibre layup. We use it for full-size components for the mock-up space model of the real car that we build throughout the winter. We can make brackets, we can make electrical boxes for wiring harnesses. We also have further RP technologies in-house that we use for different applications, and we outsource to service bureaus as well to take advantage of the technologies that we do not yet have in-house. If I could hand back to Tom now.
Great, thank you, Patty. So now I'm going to talk a bit about our SLA printer offerings, and Patty alluded to this earlier. The system that you see on screen right now is the ProX 950, which is the most current version of the printers that Force India is running and that you saw in the photo there of their rapid manufacturing center. So most of us here on the call are going to be familiar with SLA. It's the original and still considered the gold standard in all of 3D printing. And adopting this technology really lets you transform how you not only design but also manufacture your components. And you'll see throughout the set of slides that I'm going to be showing some images. And sometimes you'll see images of real big parts like this car dashboard. And then sometimes you'll see close-in shots of parts showing the very fine details and the snap fit capability of parts that are printed on SLA. And that just goes to show that those tiny features that you see in the close-in shots are just as accurate on one side of the dashboard as they are all the way on the other side of the dashboard. And that's one of the amazing capabilities of SLA, is that even over a very large part, we're able to hold exceptional tolerances with exceptional surface quality throughout. So why choose 3D Systems SLA? Well, it supports the broadest range of applications of any 3D printer. As Patty was talking about earlier, it offers the best surface finish and accuracy and detail, especially over very large parts. It's critical that when you're looking at printers that you don't just evaluate one specific feature and its accuracy, that you look at the entire part and make sure that over the size of parts that you're printing, that you maintain the appropriate level of accuracy over the entire part. SLA has the most material choice with a variety of really different engineering properties among plastics. We offer superior material properties in our Acura and VisiJet material lines for SLA. These printers are very fast. And in terms of making precision plastic parts, there's no faster technology on the market today than SLA. And these systems are very economical to operate. They have real low per part costs because they're very efficient with material use. There's very little waste involved in the printing process that SLA uses. And because of all of this, we offer the broadest range of applications of any type of precision 3D printer, from functional prototypes to ceramic parts. And ceramic is what what Patty was talking about using the Acura Bluestone and the Acura Ceramax materials are filled composite materials that give you really great rigidity and stiffness blended with a resin or a plastic type material together. You can make casting patterns from SLA parts. Parts are very durable. We offer biocompatible materials. There are high temp materials. There are tough materials, and there are optically clear materials available in SLA. And SLA offers the best surface quality, period. 3D Systems SLA is well known for its excellent surface quality, both in terms of smooth surfaces and sharp edges everywhere on the part. In fact, SLA offers surface quality that rivals the best CNC machined parts, satisfying the most demanding users. And the excellent surface quality of SLA parts dramatically reduces the post-processing time needed to generate smooth surfaces, which means parts are ready to use sooner, parts are lower cost as well because you save on labor. So there's not much sanding, polishing, that sort of thing that's necessary on these parts, whereas you can find that on some other 3D print technologies, that to get the surface finish you want, you've got to spend quite a bit of time post-processing the parts. Have a look for yourself at some of these parts. Surfaces are excellent, both up-facing as well as down-facing. So you don't need to make compromises on any surface of your product or component. In terms of precision and detail, take a look at this electronic connector. You can see walls as thin as 250 microns, 0.25 millimeters, printed perfectly with SLA. In this case, these electrical connectors are built as initial series runs of up to 2,000 parts on SLA by our customer, which is an automotive supplier. And that saves them tens of thousands of dollars in tooling modifications as they're ramping up production. And the image on the right, you can see here of a gear. You can see it being held in someone's hand and just how small that is. The teeth on this particular gear are just 125 microns wide, which for those of us in the States, that's about 5,000ths of an inch. Again, SLA offers the most material choice. We've got polypropylene class materials, ABS class materials, durable, tough materials, clear materials, high temp, and specialty, which includes biocompatible and various other capabilities. There's more than 24 materials offered on SLA systems. So buying an SLA system doesn't lock you into just one or two or three material choices. The materials are each distinct from one another, so they cover a wide array of application areas. They're not just different by color or rigidity, they are each engineered to cover very specific applications. We've got great material properties on SLA parts. In fact, every one of the materials that we offer is engineered to meet very high performance standards. For example, our ABS class materials are very tough and have ABS-like mechanical properties in all three axes, which is better even than systems that use ABS plastic as their material, because those are not equally strong in all three axes. When they're laying down layer by layer, you get delamination effects, which cause weakness in the Z direction. SLA parts hold up very well over time and over temperature variation. Another key thing to think about as you're looking at different printers on the market, you know, a part that's just come out of the printer versus a part that's a few years old can be very, very different. And if you need your parts to last for any period of time, more than a few days, you need to consider the effects of aging and ask the vendor that question. Again, we've been talking about the ProX 950, which is the largest SLA printer available, and you can see some parts that come off of the ProX 950 here. You know, having these large parts like the dashboard or this large V10 engine cuts the time required for any assembly of parts. You don't have to print parts in different pieces and then assemble them later. You can print them all at once. It eliminates part weakness associated with attachment points between different pieces, and you get the overall end-to-end accuracy of SLA over the entire part when you're using the large system, the ProX 950. Now let me just wrap up with talking about the 4 different SLA systems that we offer. The Project 6000 is our smallest system. It offers a maximum build volume of about 250 by 250 by 250 millimeters, or 10 by 10 by 10 inches. And then we go up in size through the Project 7000 into the ProX 800 and the ProX 950, which is our big boy that is 1.5 meters maximum build size in one dimension. Now, what you'll notice is that between these systems, accuracy, resolution are all the same. So as you go up in size, you are still maintaining the accuracy and the resolution of even the smallest system all the way through. And the Project 6000 and 7000 run our VisiJet SL line of materials. The ProX 800 and ProX 950 run our Acura line of SLA materials. And between those, there are some differences in terms of material properties. So it's important to understand that the difference between a ProJet SLA system and a ProX SLA system is, one of them is in the materials that they run. And of course, you can find detailed information about all of the SLA materials on the 3D Systems website. And Patty, let me hand it back to you to talk about the outcomes that you've seen from using SLA printing.
Thank you, Tom. So, yeah, the outcome. Using 3D printing, we're able to deliver every aerodynamic idea and concept to the track, no matter how complicated it might be. This would not have been possible before we started using 3D printers. And 3D printers allow us to add downforce throughout the year. A perfect example of this would be our latest car update that we put on the car at the Silverstone Grand Prix 2 weeks ago. Early indications are that this update alone has improved our lap time by 1.2 seconds compared to last year. 3D printing has revolutionized wind tunnel testing. If we had no tunnel limitation time or no tunnel time limitations, we could test 30 pairs of FWEPs in one day. This would never have been possible without 3D printing for a team like Force India Formula 1. The materials choice gives unlimited engineering access applications, but the most significant factor is that 3D printing has reduced the idea to part lead times from weeks to days, and in certain cases just hours. Formula 1 has been referred to as rapid research and development. I would say that this is an accurate definition. We do not have months or years to develop our solutions like the automotive or aerospace industries might have. We have just hours. We can have one set of bodywork on our wind tunnel model today, and by next weekend we could have modified every piece of bodywork to try and improve its performance. To develop rapidly, we need to be able to manufacture rapidly, and 3D printing is the only solution that meets this. So thank you very much, and I'll hand back over to Tom.
Great, Patty. Thank you again. So with that, we're wrapping up the presentation, which means we get to our live Q&A session now, and I've seen that there have been quite a few good questions already streaming in from everyone. So again, if you'd like to ask a question, you can just go to the questions box in the GoToWebinar window that you should see there, and feel free to go ahead and type a question in. And we're going to do our best to get through as many of these questions as we can. We'll do about 15 minutes of Q&A, and then we'll wrap up. So with that, let me introduce my colleague Denise Kerr. Denise, are you there?
Yeah, I'm here.
Hello. All right, so Denise is joining us here, and she's going to be reading off some of the questions that have been coming in, and either Patty or myself will do our best to answer those.
If production parts are made from CRP materials and a small amount of flex is designed into the part, for example into the front end nose flex, for aerodynamic efficiencies at varying speeds, how can SLA printed parts reproduce these characteristics?
Just through, generally, I would say it's just through careful design. I mean, we look at our wall thicknesses, our trailing edge thicknesses and things like this. We're obviously running a 60% wind tunnel model. We know what the aerodynamic load is expected to be on there, so we can adjust in our design stage, we can adjust our wall thicknesses and our trailing edge thicknesses to replicate what we would see on a full-size carbon part at the track. So it's just through a bit of careful thought. I mean, we can't make the material behave differently under different conditions. We just have to sort of come up with some sort of compromise in the thickness of the material to get it to behave generally how we would like.
The degradation of the material with sun and air, was that a problem in the past?
It could be a problem if you were leaving the parts on the model for months and months and months. It could be a problem, but our development is so fast that our parts won't stay on the car for more than a few days, so we don't see problems with exposure to ultraviolet or air or temperature. We don't see issues with any of those parameters just because of the throughput of our parts.
Next question. What are the various ceramic-based materials that your company provides?
So the materials that are ceramic-based that we offer from 3D Systems are Acura Bluestone and Acura Ceramax, both of which, if you're interested in the specific mechanical properties of those materials, go to 3dsystems.com, and if you look at any one of our SLA printers, if you go, for instance, to find the Pro X950 online, you'll see a tab with material information, and when you click on the Bluestone or the Ceramax material, you'll be able to download a data sheet that's got all of the specifics for each material, and that's of course true for all of the materials that we offer.
Are there any situations when you are still using traditional CNC machining versus 3D printing?
Yes, there are. For our wind tunnel model, we have the spine, what we would call the spine, which is the main sort of structure that passes through the center of the model. This takes the weight of the whole model, so it takes the weight of all the RP bits together, it takes the weight of the wheels that are out on their suspension arms. So the actual spine itself, which is a series of boxes with lots of threaded holes in, they would still be CNC machined rather than rapid prototyped.
What is the finest accuracy that can be printed?
For us, we are operating with a 0.1 of a millimeter layer thickness and a 0.12 of a millimeter diameter, which is 0.06 of an inch laser beam. So we are getting very close to 0.1 on each of our components when they are finished, so that on our model, when we bolt a series of bits together, we like our tolerance to be within 0.2 of a millimeter.
Here's another question for Patty. I have noticed that the SLA front suspension in Formula One cars has changed drastically in form. Most cars have shifted the upper link angle, reversed, to what we were taught in engineering school. Is the reason of the SLA upper link angle due to aerodynamic efficiency?
Yes.
Quick answer. By the way, there's quite a, in addition to questions, there's quite a lot of congratulations in there on the car you're designing.
Yeah, we're just reading through those as well, so thank you very much.
Yeah. What is the part cost compared to conventional processes?
It depends. It depends a little bit because SLA efficiency comes from building full platforms of multiple parts. So if we're to build one component to build it quickly and get it through to the track or to a test in a hurry, then the cost for that component goes up. But if we're to build a platform full of components, then there are huge efficiency gains in the way the technology works, and therefore the cost can go down. So you could build one component and it might cost £300, but if you then put on the platform 10 of that same component, they might come down to £50 each because of the efficiency gains. So if we build one component and we compare it to a traditional method of manufacture such as CNC, it would be, cost would be quite similar. But if you want to make 10 of the same component, then all of a sudden SLA brings the parts down to say £50, whereas CNC, they would still remain at maybe £300 each. So SLA printing is much, much cheaper than the conventional methods because it does allow you to mass produce.
Yeah, let me add to that as well. So, you know, Patty's talking about very fast prototyping production methods, right? So fast CNC that's still very accurate versus SLA, and that's an appropriate comparison because of the quality of part that you can get out of either of those approaches. Is very similar. Of course, a lot of people ask the question, how does SLA or any 3D printing technology for that matter compare to production plastics? And the answer to that, of course, is when we're talking about tens of thousands, hundreds of thousands, and millions of parts, production methods using tooling, hard tooling, are going to be lower part per cost. But I'm sure everyone on the line is familiar with the old adage that, you know, when it comes to like an injection molded part, the first one costs $100,000, the next one costs 30 cents, right? And what we mean by that is that you're paying for massive tooling expense up front, but then you're able to make large volumes of parts. Of course, with 3D printing and SLA, there is no tooling cost, right? The technology will take any geometry you give it, and it will print it out without any tooling being involved. So when we're talking about lower volumes of parts, or where every part needs to be unique and custom, additive manufacturing, 3D printing is simply the way to go. And we're seeing that's why companies around the world have been adopting this technology as quickly as they have.
Next question. What is the best material, SLA material, to create a casting for drivetrain parts like a carrier case or differential case? And how would this compare to traditional foundry-based castings?
Patty, do you guys do any patterns for casting on your systems, or no?
Not a great deal, Tom. I was hoping you were going to answer that one.
Yeah,
no, I don't really know the answer myself.
Sure. So we have, there's a material, there's two things to keep in mind with SLA when you're building casting patterns. So, you know, first of all, there's a lot of folks doing this today. It's a very popular use of SLA printers to be able to print medium to very large casting patterns. And the material that's used is called Accura Cast Pro. It's a clear resin, similar to what you've already seen on screen in this presentation. And the way that we build it is with a specific build style on SLA, where the part is not solid. It's hollow, but it has a lattice work geometry inside, which keeps it very rigid and strong. So the patterns that you can print on SLA are actually, they're exceptionally stiff, even over large parts. So you can get away with investment casting of very large parts and hold accuracy and, you know, small feature details that you can print on into the pattern very effectively. So things like, I think the question asker was talking about transportation and that sort of thing. A lot of car companies and suppliers are using SLA to print patterns for exactly that purpose.
What is the typical time savings on production of tooling versus traditional methods for tooling?
I would say that we do make some tooling for composite layup, and we can make sort of small bits of tooling for little intricate details on rear wings and things like that. We can make that tooling in probably 3 or 4 hours, and then allow the model shop maybe 1 hour to do the finishing to the very sort of fine detail. So we could be looking at maybe 5 hours to produce an absolute really top surface finish piece of tooling. Whereas if we were to make that in the pattern shop, first of all, it wouldn't be as accurate. It would take probably take still a few hours, probably just as long to manufacture. Again, I'm talking about manufacturing one part on an SLA printer versus machining one part, so the time difference wouldn't be that different, but the part quality would be much better on the SLA. And then when we need to do a survey of those these bits of tooling, so we want slight iterations for various details on the wing, all of a sudden we can manufacture 10, 20 or 30 in the same time it would take to build 1 or 2 using the traditional method.
Here's a question. Do you see the future of rapid prototyping to replace conventional manufacturing?
I can take that one. No, I don't think that 3D printing or rapid prototyping or additive manufacturing is going to replace traditional manufacturing. It's going to do what it's been doing today, which is supplement traditional manufacturing, right? So it's rare to see one of our customers, you know, stopping using CNC or casting or forming of any sort, right? All of these other methods they continue to be useful. What 3D printing is usually being used for is to speed up the overall process. And so we don't see, you know, each approach, subtractive, additive, formative, whatever the case may be, has strengths and weaknesses. And additive manufacturing won't become, you know, I don't see a point in the future where everything will be 3D printed. I do see a point in the future, and it's already happening today, where lots of components of everything that you buy are 3D printed, and especially in areas like healthcare, we are seeing a real strong shift to where a lot of things are 3D printed, and particularly in healthcare, it's critical because every one of those parts can be custom to the patient, and that's why we see a lot of end-use production in healthcare moving to 3D printing. But no, this is not a technology that will replace. And in fact, if you look at us as a company, 3D Systems, we recently acquired Cimatron, a major CAM manufacturer, which of course is software that feeds into CNC machines. And so, you know, our own bet on the future is that digital fabrication of all sorts is where things are going to continue to head in the future. And that means additive, that means subtractive, that means all kinds of different technologies.
What is the turnaround time factor from producing a prototype part to actually putting the final part on the car?
We could build the prototype part and we could test it in the wind tunnel within probably 2 hours of it coming off the machine. Then after that, depending on what type of part it was, we could probably manufacture it in full size using the more traditional methods again, so that we end up with a carbon part. We could probably manufacture that in just a couple of days. But when it comes to whole bodywork kits and things like that, like what you will have seen at Silverstone, that takes us weeks to manufacture that because it's the whole car. So we will have issued that spec of car from our wind tunnel quite a few weeks back, and then it will have been manufactured to make the full car. So we can manufacture a one-off component in a few hours, but complete sets of bodywork still takes weeks.
Does 3D Systems provide you with all the material properties, or do you have to get the material properties in your lab?
So 3D Systems, they do provide us with material spec sheets and data sheets and handling sheets and all the stuff you would expect. But because we do put parts on our car, and if they fail, people's lives are kind of at risk because of the speeds we're travelling at, we do still carry out tensile tests on these materials ourselves to create our own selection of properties that we want to work to so that we can decide if it's suitable. But 3D will give you the information, but because of the nature of our business, we like to validate all that information ourselves anyway, and we would do that with any supplier.
How accurately can you replicate the material stiffness with SLA parts compared to the final wing part?
It's very, very accurate. Again, the SLA parts, you have to remember, the SLA parts are not being exposed to the aerodynamic load that the full-size parts are being exposed to. So they only have to withstand sort of 60% of the aerodynamic load that the real car would see. And they stand up against that very well. We get very little flex because there is the filler in the material and it's dense and it doesn't allow the part to move. So it does replicate the final wing part very accurately.
Now, final question. Are there any parts of the F1 race cars on the track that lend themselves to printed parts over carbon or machined parts?
There are parts on the car that lend themselves to printing, usually parts where you're unsure what you really need the shape to be on the day. So you put something on the car and then you decide it might need to be a bit higher or a bit lower or a bit wider. And there are little parts on the car like that where if we were to manufacture them using the traditional methods all the time, then they're going to cost us a lot of money and we won't always be able to get all the options available to us at the track. So for those parts where they're tiny little iterations on the car setup, depending on what the weather's like, what the wind's like and things like that, then those type of parts we would 3D print a survey of parts so that we've got a configuration for whatever the track's doing, whatever the weather's doing, that sort of thing. So there are quite a few printed parts on the car.
Great. I, of course, want to thank the entire Force India team, and especially Patty for spending time here with us today to share how you're using 3D printing and SLA in particular. We're really thrilled to have the team as a customer. We've got a great relationship. We really like working together with you and love seeing the really amazing stuff that you're able to do with the printers. So thank you very much for that, and I want to thank everyone in the audience for your attention as well. Hopefully it was enlightening and entertaining, and you learned something new today.